Hi everyone, welcome to gemchem. This is the video on alkanes part 2. Now if you have still not watched the alkane part 1, do watch it. I will give the link in the description box. Now we will deal with the chemical properties of alkanes. So here we will deal basically with halogenation of alkanes and a named reaction known as Finkelstein reaction. So let us start. Now see, halogenation, we will first deal with chlorination, that is addition of chlorine to alkane by replacement of a hydrogen present in it. Now let us see. Now this chlorination is brought about with the help of chlorine and light, heat or catalyst. Now it depends on the amount of chlorine used and mixture of all types of compounds, chlorine compounds are obtained as there is difference in reactivity of primary, secondary and tertiary hydrogen atoms. Now what is the order of case of substitution? Tertiary hydrogen, then secondary hydrogen and then primary hydrogen. So what is tertiary, secondary and primary hydrogen? Now see, when a carbon is attached to 3 carbons, then the carbon is known as tertiary carbon atom and the hydrogen attached to that type of carbon atom is known as tertiary hydrogen. And again, if a carbon is attached to 2 carbons, then that kind of hydrogens present, this and this carbon, these hydrogens are known as secondary hydrogens. And if a carbon is attached to 1 carbon, the hydrogens present in that carbon is known as primary hydrogen. That is this and this are the primary hydrogens. Now let us see an example. Now see this one. This is an example where we use primary hydrogen here, that is present here, and a tertiary hydrogen that is given in the green color. Now see, observe this thing very carefully. We know that the reactivity of tertiary hydrogen is more compared to that of the primary hydrogen. But here the yield is different. For this case, for tertiary, the yield is basically 33%, and for 1 degree it is basically 67%. So what does it mean? It means that there is another different factor which is involved in the yield. Now let us see. Now tertiary hydrogen is basically replaced 4.5 times faster than the primary hydrogen. This is an important factor. Now how it is obtained, this factor we will see. Let us observe. Now see, 67% of primary hydrogen is giving the yield of this one, this product, right? Now see how many primary hydrogens are present. 3 here, 3 here and 3 here. So there is 9 primary hydrogen, right? So 9 primary hydrogen gives rise to 67% of product. So chance for each hydrogen will be, what will be the chance for each hydrogen? 67 divided by 9, that is chance for each hydrogen becomes 7.4, whereas the chance for one tertiary hydrogen that is present here, in this case there is only one hydrogen, right? One tertiary hydrogen. Now what is the chance for it? Its chance is 33%, so chance is also 33, right? So chance is also 33, so this is greater. See, the chance of this tertiary hydrogen is greater than the primary hydrogen, so the 4.5 time factor comes from here, that is 33 divided by 7.4 gives us basically 4.5. So we get a result that is for primary hydrogen, that is what we see here. The primary hydrogen, though the yield is greater but the rate is slower, whereas for tertiary hydrogen, though the yield is less but the chance of formation and the probability and the rate is much greater. Now we will see the mechanism for the reaction. So let us see what is the mechanism for halogenation reaction, specifically for all halogenation reactions. So see this one. Now if suppose we take a halogen as X2, then in presence of light, UV light or photon, it breaks up into radical, that is to X dot. That is, if a bond is like this, then this is broken from between. One electron is here and one electron is here. So we get this one. Next, this step specifically is known as chain initiation, whereas next part is chain propagation. We will learn about propagation, how it propagates. Now in next step, we basically take the alkane plus the X dot, and from there we obtain R dot plus HX. That is, this bond breaks up to give R dot and this part attaches with this one to form HX, whereas now this R dot reacts with the halogen moiety to form Rx and then X dot. Now this is a process where halogenation takes place, and this is the mechanism of halogenation. Now we will see for the reaction which we have already learnt. Now see this reaction, we have seen this previously. Now here it is 67% and here it is 33%, right? Now we will see the reaction mechanism for this particular case. Now see what is the reaction mechanism. Again same thing, we know that on giving light, chlorine breaks up into chlorine radical. Now there is two type of radical formation in case of alkane. One is primary and one is tertiary. So let us see, this is the alkane, right? Now first we will see for primary. If one of the primary hydrogens present here is abstracted, we will get a radical like this. See once, that is, we will get this radical CH2 dot, one hydrogen gone, that is hydrogen dot gone. Now this reacts with this chlorine to form the product which is obtained here. Now in the second case, that is for the case of tertiary one, we will see that this is 67 and this is 33. Now we see for tertiary one, that is CH3, CH3 and CH3. Now here is a hydrogen which is gone, right, leaving behind a radical. Now we get the data as CH3, CH3, CH3 dot. Now this dot here reacts with this chlorine dot to form the product obtained here. So this is the basic mechanism of halogenation. Now let us see our next part. See, for the bond energies, while breaking this bond which is 99, there is a release or decrease of energy, that is minus 3 kilocalorie per mole. As for this also decrease in energy. Now what does it mean? That when reaction takes place, there is a release of much of heat. When heat is released, the product becomes more stabilized and becomes less in energy. So for chlorination, both steps are exothermic and product will have less energy compared to the reactant, as there is loss of energy, and thus the transition state will be reactant like. What do we mean by transition state to be reactant like? Let us see. Now see, for the same reaction, here the transition state is reactant like, that is more near to the reactant. Now for formation of tertiary carbon radical, there is least requirement of activation energy rather than primary one. So the reaction rate for this one, for formation of this radical, is much more than in case of this, which is primary one. Now let us see our next part. Now let us see an example. Now see, here also there is same type of thing, but we prefer to substitute the tertiary one. So we get two types of product. This is a chiral molecule to give a racemic product, 50:50 ratio to form 1:1 chiral products. Now see what is the radical form in this case. Basically the radical formed in this case is here CH3 and here dot, and here CH3, here hydrogen, here also Cl, and here two hydrogens. Now a chlorine radical, free radical, chlorine free radical can attack from above the surface or from below the surface. So here attack from above the surface, here from below the surface. So stereochemistry is different for two different molecules and the yield is 50% and 50%. Now let us go to the bromination part. Now see, here the bromination takes place similarly as chlorination, but the method is less vigorous, and since less vigorous, that means that bromine is less reactive, so more selectivity in the reaction pattern, and also it is seen from this reaction yield. We can see that 99%, more than 99% yield for the primary carbon atom, as the statistical factor is greater here. Now see, here this one is less than 1%, though the rate of this reaction is more, but let us see what happens. Now see, for this kind of reaction in bromination, first step is endothermic, that is there is gain of energy. Now if gain of energy occurs, then the product will be in more upper part of the energy valley for energy profile diagram, and the second one is the exothermic step. Now less reactive reagents, so more selective, and the rate determining step is considered to be the first step, which is the endothermic one. Okay, this is important, and the transition state is product like, because this is more near to the product. Now see here this one, the energy is again required is less for activation, whereas for the primary one energy is more. So rate for this one, rate for 3 degree will be more, though the yield is less, because there is only one hydrogen which is tertiary, whereas there is 9 hydrogen which is primary. Now let us go to our next slide. Now see, fluorination, basically direct fluorination is impossible as it is highly explosive. Special conditions are required for preparing its derivatives. See this, both steps are highly exothermic. Highly exothermic means more and more release of energy, more and more release of heat energy, and there is probability of high explosion. Now see, Iodination basically is a reversible process in these cases and is carried out in presence of HiO3, HNO3 and HgO, because these oxidizing agent destroys this Hi, which causes the reversibility. So by Le Chatelier's principle, if this Hi is being removed, the reaction will move towards the right hand side for more and more production of Hi. So Hi is removed by this oxidation method. That is 5 Hi plus HiO3 produces 3 I2 plus water. Now let us go. Now what is Finkelstein reaction or Coulomb-Finkelstein reaction? Now this is the reaction which basically is a method to do iodination in some different techniques. Now what we have to do, we have to take an alkyl chloride or an alkyl bromide and react it with NaI, that is sodium iodide, in methanol or in acetone. Now they produce a substitution reaction, that is Ri. It produces basically Ri and NaCl or NaBr. Now what is the advantage of this reaction? First of all, this reaction takes place by SN2 pathway. That is, when suppose this one comes, that is I minus comes, we can write NaI as Na plus and I minus, right? Now this I minus, when attacks, it attacks from backside and the chlorine Cl minus goes away, that is chloride ion goes away. Now this advantage is that for this reaction is that I minus is a good leaving group. So when I minus is a good leaving group, we can use this reaction for different purposes. It can be used to produce alcohols, to produce alkanes, because by dimerization we can produce alkanes. So I minus is a good nucleophile as well as a good leaving group. So it has an utility for this reaction. Another utility is this alkyl iodide can be easily extracted from the medium as NaCl. This Ri can be easily extracted from the medium as NaCl and NaBr can be removed as they are both insoluble in acetone. So we can easily remove them, right? So this is the best method in which we can obtain alkyl halide. So this reaction is basically known as Finkelstein or Coulomb-Finkelstein reaction. This is a process of producing alkyl iodide without any problem of reversibility. Clear? Now this much for today. Thank you for watching. Do not forget to subscribe my channel, like, share and comment.